Chapter 13, Solutions. This is a very important chapter to understand chemical solutions. We begin by looking at the tragedy in Lake Nyos, Cameroon, West Africa. It was in 1986 that all of a sudden carbon dioxide bubbled out of the lake and flowed into the valley. The valley occupied the whole atmosphere with carbon dioxide, hence people or any living thing had no resource to breathe oxygen. This happened when the layers of the lake were disturbed and the carbon dioxide came out of solution due to an decrease in pressure with these lethal consequences. First of all, Lake Nyos is water-filled volcanic crater, and the volcanic rock beneath the lake produces carbon dioxide that seeps into the lake through the volcano's plumbing system. The concentration of carbon dioxide that can build up in the water increases with increasing pressure. The great pressure at the bottom of the lake allows a huge concentration of carbon dioxide. Over time, the carbon dioxide and water mixed at the bottom and became so concentrated that some of the gas escaped. The rising bubbles disrupted and destroyed the stratified layers of the lake, causing the highly concentrated carbon dioxide and water mixture at the bottom to have a pathway to rise very rapidly. So the drop in pressure on the mixture released more carbon dioxide. So since carbon dioxide is heavier in the air, once freed from the lake, it traveled along the sides of the volcano into the nearby valley, displacing air and killing more than 1,700 people and at least 3,000 head of cattle. Well, what is a solution? Well, solution is a homogeneous mixture. That means it's the same throughout. And the carbon dioxide and water mixture at the bottom of Lake Nyos was an example of a solution. Solutions are common. Most of the liquids and gases that we encounter in everyday life are actually solutions. The ocean itself is a solution of salt and other solids dissolved in the water. Blood plasma is also a solution. A solution may be composed of a gas and a liquid, like carbon dioxide and water of Lake Nyos, or a liquid and another liquid, or a solid and a gas. Any other combinations. Here are some common types of solutions. A mixture of air is a gaseous solution, a gas with a gas. Liquid solution would be a gas with liquid, that's like soda water. Liquid, vodka is a mixture of ethanol and water. Seawater. And solid solutions are alloys. A mixture of copper and zinc is brass. Solutions, homogeneous mixtures. Let's use a little terminology so we can quickly understand what the components of a solution. A solution, and I abbreviate SN after the first letter and the ending letter, has two components. The majority component is usually called the solvent, ST, or the minority component is called the solute, SE. Because water is so abundant on Earth, it is a common solvent that forms aqueous solutions of many things. Other solvents are used in the laboratory and in industry, especially to form solutions with nonpolar solutes. Common laboratory solvents are water, and these are polar, and acetone and methanol, and nonpolar hexane, diethyl ether, and toluene. It's important to remember that like dissolves like. So polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Forming a solution of solid sodium chloride, which is ionic in nature when dissolved. In the solution of sodium chloride, the sodium ions are attracted by the negative pole of the water molecule, and the chlorine ions are attracted by the chloride ions are attracted by the positive pole of water. So in fact, if this is solid sodium chloride, the solvent then removes the ions, and the ions are in a solvent K. Sodium ion surrounded by the negative pole of water, chloride ion surrounded by the positive pole of the water molecule. The solubility of the compound is defined as the amount of the compound, usually in grams, that dissolve in a certain amount of liquid. The solubility of sodium chloride at 25 degrees is 36 grams of sodium chloride per 100 grams of water. A solution that contains this amount is called saturated. A saturated solution holds the maximum amount of solute under the solution conditions. If you add one more pinch of the solute, it will not dissolve. An unsaturated solution is holding less than the maximum amount it could hold, and so if you add a pinch of the solute, it will dissolve. A supersaturated solution is one that's actually holding more than it should have. And so if you put a pinch of the solute, normally it will precipitate, and all the extra will come out of a supersaturated, like a snow falling. How solubility varies with temperature. Very important to understand that generally as you increase the temperature, solids dissolve a little better. Looking here at how to interpret this graph is important. This has its solubility and this has the temperature. And we look at sodium chloride and we see really increasing the temperature doesn't increase its solubility. For instance, we can see that at 90 degrees centigrade, actually 40 grams of sodium chloride will dissolve in 100 grams of water. However, look at some of these others. For instance, potassium nitrate. It becomes almost infinitely soluble as you raise the temperature. Or potassium chloride increases quite a bit by warming. Let's look at solutions. Electrolyte solutions contain dissolved ions, that is, charged particles, and therefore they conduct electricity. Non-electrolyte solutions contain dissolved molecules, and they're neutral, and they do not conduct electricity. So this is kind of a visual idea of electrolyte with ions and a non-electrolyte just with molecules, non-charged particles. If you might like to try to make some rock candy, you can simply prepare a saturated sucrose solution at an elevated temperature and dangle a string in the solution and leave it cool and stand for several days, and the crystals will grow and you will have very sweet rocks of crystals that can be eaten. The solubility of gases is kind of just the opposite of solids. Generally, gases' solubility decreases when you increase the temperature. And you can see this if you begin to heat ordinary tap water on a stove. You'll see bubbles that are not related to boiling, but from the gases coming out, mostly dissolved air. But once you see the bubbling, the big bubbles, those then are actually vapors of water. Warm soda fizzes more than cold pop. As you can see, the fizzing over here of a warm soda means that the temperature is high enough that the dissolved carbon dioxide comes out quicker, less soluble. Henry's law talks about high pressure of a gas above a liquid. The solubility of a gas increases with increasing pressure. So here's increasing pressure, hence more soluble, more gas dissolves. This is useful in hyperbaric therapy, which involves exposure to oxygen at a higher than atmospheric pressure, and it may be used to treat hypoxia or low oxygen supply in the tissues. Or pop fizz, a can of soda is pressurized with carbon dioxide, and then when the can is open, the pressure is released, lowering the solubility. So this is why, in fact, when you open a can of pop, it fizzes. We need to talk about solutions and their concentration, since it's a mixture. the amount of solute in a solution changes, so it has to be designated. One way of designating it is mass percent. Mass is a number of grams of solute in 100 grams of solution. A very easy definition. For instance, a solution with a concentration of 14% by mass contains 14 grams of the solute in 100 grams of the solution. To calculate mass percent, you simply divide the mass of the solute by the mass of the solution and then multiply by 100. So let's suppose that we want to calculate the mass percent. Well, here's the kind of formula. Mass of the solute, and this mass of the solute plus the mass of the solvent adds together to be the mass of the solution times 100. In addition to this kind of calculation, there's such a thing as parts per million. Percent is parts per 100. Parts per million, parts per billion. So these calculations all look like this. Grams of solute over grams of solution times 100, that's percent. Grams of solution over grams of solute over grams of solution times a million, that's parts per million. Easy to calculate. We can use the mass percent of the solution as a conversion factor between mass of the solute and mass of the solution. The key to using mass percent as a conversion factor is to write it as a fraction. If you have something that's a certain percentage, then you say 40%, then you say you have 40 grams of solute in 100 grams of solution. And then this item can be used as a conversion factor. For instance, the water at the bottom of Lake Nyos contain 8.5% carbon dioxide by mass. Determine how much carbon dioxide in grams is contained in 28.6 liters. Well, these are the given information. And you have to know that the density of this solution is 1.03 grams per milliliter, and also remember that 1,000 milliliters is equal to a liter. So find the grams of CO2. The solution map is take the liters of solution and convert it into milliliters. Using the density, convert the milliliters into grams of solution. Using the percentage, convert the grams of solution to grams of carbon dioxide. So it looks like this, 2.86 liters, a milliliter per 1,000th, or you could even say 1,000 to 1 if you want. Density and percentage turns out to be 2.5 times 10 to the 3 grams of carbon dioxide in this volume of solution in the lake. In the United States, the presence of contaminants in water supplies is monitored by the EPA. And they set limits. These are called maximum contamination levels, MCLs, for each of the dirty dozen in food and drinking water. These are some of the dirty dozen, mostly insecticides, various things. The maximum concentration, for instance, of dioxin is 10 to minus 8 milligrams, or more easily said, 2/1000ths of a milligram per liter for chloridane. Another way of specifying concentration is molarity, and this is a very important one for chemists. Molarity is defined as the number of moles of solute per liter of solution. Note that molarity is moles of solute per liter of solution, not liter of solvent. To make a solution of specified molarity, you usually put the solute into the flask and then add water to the desired volume of the solution. It's very easy. For instance, how would you prepare a 1.00 molar sodium chloride? That would be abbreviated 1.00 capital M. So what you need to do is put 1.0 mole into the flask, and we know the molar mass of sodium chloride is 58.44, so you weigh out 58.44 of the solid and put it into the flask. Then you add some water, usually only part of the water, and you swirl. These flasks are easy to swirl. And then you dissolve it, and then you continue adding water up to below the mark, and when you get near the top, then you use a wash bottle to add carefully to get your bottom of your meniscus to be exactly in the mark. You mix it very well, pour it out into the bottle, and label it as 1.0 m sodium chloride solution. Suppose you were asked to calculate the molarity of solution made by putting 15.5 grams of sodium chloride into a beaker and then adding water to make exactly 1.50 liters. This is very easy. First of all, consider the 15.5 grams and convert that to moles. And that's easily done by using the molar mass conversion factor, dividing. So we end up with equal to 2.2652 moles of sodium chloride. Then we look at the definition of molarity, capital M. We need the moles of solute. Okay, we have it. We need the liters of solution. Okay, we have it. So we simply do that division, and this is a 0.177 molar solution. And we're going to keep it to 3 sig figs because the given amount here is 3 sig. Suppose we want to determine how many grams of sucrose, this is its formula, are contained in 1.72 liters of a 0.0758 molar sucrose solution. Well, basically the solution map is you take the liters of solution, and convert it to moles using the definition of molarity, and then the moles to grams using the definition of molar mass. So the fact that this is the molarity, 0.758 moles of that per liter, and this is the molar mass, 342.34 grams. Here's what the setup looks like. Start with the volume, 1.72 liters, convert that to moles, and then continue in converting the moles to grams, and the solution is 446 grams of sucrose, which of course the 3 sig agrees with the 3 sig given. Solution dilution. This is a very important process that we use all the time in lab, where we take a more concentrated stock solution and dilute it to a solution of lower concentration. In general, this is easily done by considering that our beginning solution, M1, and our volume 1 are our more concentrated ones, the stock solution, and this then is our diluted solution too. So where this is, M1 is the molarity of the stock solution and the volume of the initial concentrated solution, which you often do not know what volume to take. And then you know the molarity that you want of your dilute solution, and you know what volume you want of that. So you end up knowing the molarity of the dilute you want to make and its volume that you want, and you know then the molarity of the concentrated, and the unknown is what volume of the concentrated should I take. It works like this. You simply substitute the moles of solute times the volume, which is equal to the moles, and you notice that M times V is equal to moles, so you notice the moles of this equal to the moles of that. So in fact, what doesn't change is the number of moles. Let's have a word about laboratory safety. Notice when you dilute acids, always add the concentration of concentrated acid to the water. Never add water to concentrated acid. Sometimes people use the saying, acid to water, really you oughter, the other way around could put you in the ground. So in fact, acid to water. Suppose you're asked to prepare 5 liters of a 1.5 molar potassium chloride, and you have a stock solution that is 12 molar. So very easily, you know that you have you want 5 liters, that's of the dilute solution, and the dilute solution is 1.5 molar, and the concentrated solution is that. So you just set it up in this way. V1, you simply divide through by M1. So M2, V2 divided by M1. So simply substitute your numbers in and you'll end up with a thing that says take 0.625 liters of your concentrated solution and dilute it up to 5 liters. Here's what that would look like. Taking 0.625 and putting that into a 5-liter flask. It's a very big flask. And then add the water. Okay. And the water, then you add it up to almost to the mark, and then you finish it off by diluting exactly to the mark, and you'll end up then with 5 liters of the dilute solution, 1.5 molar. We also have things involved, solutions involved in chemical reactions. And so this is a change from stoichiometry of mass. Usually we have a volume of a solution and we can use its molarity to get moles. Then we look at a balanced equation, we get moles of A to get moles of B. Once we have moles of B, we can then calculate the volume then of B. So this is a useful calculation. For instance, we might ask ourselves, how much 0.1 molar sodium hydroxide solution do we need to completely neutralize 0.225 liters of 1.75 molar sulfuric acid? Here's the balanced equation. Sulfuric acid plus 2 moles of sodium hydroxide produces this salt and 2 moles of water. Here's the solution. Take the liters of sulfuric acid, which you have is 2.25, and then convert it to moles using the molarity of the sulfuric acid. And then when you have the moles of that, use the stoichiometry of the equation, 2 to 1, and then you'll get moles of sodium hydroxide. Once you have moles of sodium hydroxide, simply divide that by the volume of sodium, by the molarity of sodium hydroxide. It's just moles per liter. So these will cancel, and you'll end up with the liters of solution. Here's a setup if it might help to do that. Here's the liters of sulfuric acid, its molarity to get moles of sulfuric acid, its stoichiometry to get moles of sodium hydroxide, and finally using the moles of sodium hydroxide, this is the inverted conversion factor of the known concentration of sodium hydroxide, 0.125 moles per liter. We had to invert it so it would cancel, and we end up with 0.630 liters of sodium hydroxide needed to exactly neutralize that. One last topic in regard to solutions are a kind of a mysterious item called colligative properties. And these are freezing point depression and boiling point elevation, and also osmotic pressure. First of all, colligative properties means that it depends upon the number of particles in solution, like collegiate, collection. So if we add a non-volatile solute, one that doesn't readily evaporate, to a liquid, it extends the temperature range over which it remains liquid. For instance, if we put salt in water, the freezing point is lower. That's why we put salt on the sidewalks in winter, so that the ice will not freeze. The freezing point will be depressed. Or if on top of the mountain we want to cook our food in a little hotter water, we may add salt to the water, and it will elevate the boiling point. So freezing point depression and boiling point elevation depend only on the number of particles, and these are colligative properties because of that. Freezing point depression, freezing point of a solution contains non-volatile is lower. The concentration of the solution is usually expressed in molality, abbreviated small m. Definition of molality is moles of solute per kilogram of solvent. Note that molality is very different, is a different definition than molarity. The only difference is this one letter, an L instead of an R. So you might be asked to calculate the molality of a solution containing 17.2 grams of ethylene glycol, and it's dissolved in 0.5 kilograms of water. Ethylene glycol, of course, is an antifreeze. So you're given the grams of ethylene glycol and you're given the kilograms of solvent. So molality, as you remember, is moles of solute divided by kilograms of solvent. You already have the kilograms of solvent. You simply need the moles of solute, which is done by using the grams of solute by its molar mass, and you'll get moles. So we substitute in the moles, and we do the calculation, and we see that this is a 0.554 molal solutions. So the freezing point depression formula is this one. The change in the temperature freezing, that will be lower, is the molality times the Kf. So these are the definitions. The Kf is known for water. For water, the Kf is 1.86 degrees Celsius kilograms of solvent per mole of solvent. Or another way of saying it is 1.86 degrees Celsius per molality. So that when you multiply the molality times that, you end up with a degrees Celsius change. So we have a 1.7 molal ethylene glycol, automotive antifreeze, and so we already know its molality. So we just say it times 1.86, that's the Kf. This is the molality, cancels, and we end up that we get a change in temperature of 3.2 degrees Celsius. So since ordinary water freezes at 0 degrees Celsius, we subtract off this change, and we see that we have lowered the temperature freezing to minus 3.2 degrees Celsius. So the water in your radiator will not freeze and break the radiator. Boiling point elevation is a solution contains a non-volatile solvent. So in automobiles, antifreeze not only prevents freezing of the coolant within the engine blocks in cold climates, but it prevents boiling of the engine coolant in hot climates. Here's the formula again. The change in temperature boiling, this time it's going to be higher, is the molality times the Kb. And these are your definitions, and we know the Kb for water. It is 0.512 degrees Celsius per molal. So the boiling point of a 1.7 molar ethylene glycol automotive antifreeze solution would be 0.78. It's going to rise 0.87 degrees Celsius. So instead of boiling at 100, it'll boil at 100.87 degrees Celsius. Finally, osmosis. This is an interesting idea. Why if you're stranded in the ocean, you can't drink the ocean water because it's salty. The flow of a solvent, usually water, from a less concentrated solution to a more concentrated solution. This occurs when solutions of high concentration are trapped by a membrane, and it'll flow toward a lower concentration of solute. Let's take a look at the picture of it. Seawater is thirsty solution. As it flows through the stomach and intestines, seawater draws water out of body tissue, promoting dehydration. That's because what happens is that these are the tissues right here, and this is the digestive system, and what happened is the water comes out of the tissues to dilute the salt water that you just drank. In an osmosis cell, you can see this happening. What happens is here's a semi-permeable membrane. That means it only permits the smaller water molecules, not the larger blue solute molecules. So what will happen is that you have the water molecules moving in, and you see this level rises above that level. This difference in level is called the osmotic pressure. Osmotic pressure. Let's look again at osmotic pressure and understand that it is related to, it is a colligative property, and it depends upon the number of particles in solution. More concentrated the solution, the greater is osmotic pressure. And membranes of living cells act as semi-permeable membranes. If you put a living cell into seawater, it loses water through osmosis and becomes dehydrated. Looking at what could happen to red blood cells. This is in a normal solution. The osmotic pressure is equal to the surrounding fluid, so the cell is normal. In B, the red blood cells are in pure water. So inside of the cell is more concentrated, and so water tends to go into the cell. And this then, of course, can cause the red blood cell to break. However, this is red blood cells in a solution that is more concentrated out here, so water flows out of the cells, causing dehydrated red blood cells. Solutions that have osmotic pressure less than that of bodily fluids are called hypoosmotic, and they tend to pump water into the cell. Solutions that have high osmotic pressure greater than that are called hyperosmotic, and they tend to take water out of the cells. Intravenous solution must have the osmotic pressure equal to that of body fluids. That is, they must be isoosmotic. When a patient is given IV in a hospital, the majority of the fluid is usually at an isoosmotic saline solution, a solution that contains 0.9 grams of sodium chloride per 100 milliliters of solution. That's hypoosmotic. Remember that osmosis is the flow of water from a low concentration to a high concentration through a semi-permeable membrane. So in this chapter, we've learned many skills: calculate the mass percent, use mass percent in calculation, calculate the molarity, capital M, use molarity in calculation, calculate solution dilution, M1 V1 equal M2 V2, and use dilution stoichiometry in reactions, calculate molality, moles of solute per kilograms of solvent, and calculate changes of freezing point depression and boiling point elevation. So, in fact, chemists have solutions.